Swayam Prabha. Digital India. Educated India.
In conceptual framework is there is an input buffer which contains the words of the sentence, and then the parser or the oracle decides that every state of the machine consists of a stack and the input buffer. So these are the words in the sentence, and the stack contains the words again, but you look at the top two words in the stack, okay, and make decision as to which operator to apply, left arc, right arc, or shifting. We have also said that this decision is also used, or the same configuration is used to also decide what should be the label on the arc. Now, this is the primary framework. Okay, the other primary framework is graph based, which we'll take a look at very soon. And the dependency relations are the uh, list of dependencies which need to be used when we produce the labels on the dependency arcs. So just to remind you what goes on, the sentence is book me the morning flight. These examples and a lot of this material is from Speech and Language Processing, Juravsky and Martin, chapter 15, 2019. Chapter 15 is downloadable from the web. Now, initially there is root on the stack. We transfer the first word in the sentence, book. And that leaves me in the input buffer, me the morning flight. Book me the morning flight. Book has shifted to stack. Now look at the top two words, book and me. Now book is the main verb. How do I know this is the verb? Book is also a noun. I assume that previous NLP layer, namely part of speech tagging, has given me the correct part of speech tag in the context. So book is a verb. Now for between book and me, create a right arc. So that is an arc going from book to me, where it shows that me is a modifier or dependent on the word book. Okay, and you know that me will be the beneficiary of this booking activity. I will benefit from the booking of the ticket for the morning flight. And what is being booked? Flight is being booked. Okay. Now, after I do this right arc setting up, then me disappears from the stack. Okay, the modifier always goes out first from the stack. Always the modifier goes out. What is the reason? If I remove book from the stack, then you see I've taken the root of a subtree which is rooted on book, because book also has other dependents. The flight, for example, will be related to book by object relationship. And then flight is again the head for the and morning. So surely when flight comes onto the stack, then it will have to wait. It will have to wait because morning and the, which are the modifiers for flight, they will also come to the stack, and then they will be linked, and the modifiers will disappear from the stack, leaving book and flight on the stack, and that will lead to setting up book and flight, the DOBG relationship between book and flight. So you see, it is important to first cover all the dependents or all the modifiers. Okay, so this kind of systematic staged operation of linking or the modifiers and pushing them out of the stack demands that the sentence is projective. Okay, otherwise there will be problem, and it is instructive for you to work out the stack for projective and non-projective sentences. In particular, please put this as an exercise, Satyam, or somebody who is in charge of taking the exercise today. So if you have this projective and non-projective sentences, this is so the athlete runs fast who also jumps high is non-projective. The athlete who also jumps high runs fast is projective. So the exercise is run these two sentences on for the transition based dependency parsing and see what problem appears in case of non-projective sentence coming onto the buffer. Okay, what will be the exact problem? So if you're very clear about the transitions happening, then it will be easy for you to answer. So going back to this discussion. So it is important that we know that a word will have dependents, okay? And those dependents are coming first, okay? The morning flight, for example, the and morning will come to the stack first, and flight will come after that. So when the modifiers come, you will have to wait for the head to arrive. Okay, when the head has arrived, you progressively link the modifiers until only the head remains, and that head is now linked with its own head, because a word can have double role of being a modifier and a head. Flight, for example, is a dependent word for book, but flight is also a head for the and morning. So the words can have double role. They can be both head and modifier. So this is the basic principle, that we first pop out of the stack the modifiers and then finally come to the last configuration, which is the root. The root, when removed from the stack and the word list being empty, is the condition for successful termination of the algorithm. So I again emphasize for you to develop the insight into the notion of projectivity. Why projectivity is important? For the reason of systematic working of the transition-based parsing. That restriction is not so stringent when we move to graph-based parsing and probabilistic dependency parsing. So that is the importance of probabilistic parsing algorithm, because they are more robust. Okay, what we are discussing so far is essentially a rule-based approach to dependency parsing. So whatever I said, I hope was audible, and this point, that modifiers have to first go from the stack followed by the head. Okay, that is the crux of the algorithm, and therefore this is intimately linked with projectivity. So these 2 points should come on a slide. Jyotsna, if you are taking the notes, or whoever is in charge of inserting additional slides, please note this. The 2 points have to come prominently. The modifiers have to go from the stack before the head, and for this to happen, the projectivity of the sentence is important. These 2 points very clearly should come. And the 2 important points I made, I hope was audible. Okay. Now we proceed and see that whenever there are 2 words on the stack, there is a decision to be made about left arc, right arc, or shifting. So now book me the morning flight. I decide to set up the arc. Uh, I set up the arc between book and me, and shift me, the modifier for book, out of the stack. So me has gone out of the stack. So notice that since me has gone out of the stack, there is no way you can set up relations with me. This is a greedy algorithm. Okay, so a word coming out of the stack and going to the relation repository will not be examined again. So this is a greedy algorithm. There is no scope in the classical transition based parsing for backtracking. Okay, but there have been modifications later, and in particular, probabilistic parsing, of course, is a totally different approach. Now, now I have the words the morning flight. Decide to shift. I decide to shift. Why? Why not set up a relation between root and book and be done? No, because the word list is not empty yet. Therefore, this is a feature for decision making. Root to book, I cannot set up a relation if the word list is not empty. Okay, so this becomes a feature for the decision making algorithm. Okay, so you can begin to see that some features are emerging. The state of the input buffer, the state of the stack, the actual words and part of speech on the stack, they are the guiding features. Now I have shifted that exposes morning and flight. Can I set up a relation between book and the? No. Okay, how do I know that I cannot set it up? The cannot be a dependent for book. Okay, the cannot be a modifier for book. How do I know that? This requires again the signals from the feature. The is a determiner, book is a verb. Okay, uh, verbs do not link to determiner directly. So you see, this is a rule, and these are the features which are used. The is a determiner, book is a verb. How can a determiner cannot directly link with a verb? So this is the decision, and based on the features of part of speech of the and part of speech of book. Okay, so you can see why part of speech tagging is important before we set up the dependency parse relations. Now I shift morning operation on book and the linking them. Morning is shifted, and then I have the and morning. Okay, uh, I could I link the and morning? uh, the decision maker or the oracle says that no, you have to still shift. But why? Because there is a word coming after flight. But the and morning are very frequent bigrams in the corpus. In NLP, you do see the morning, the evening, the noon, the dusk, a lot. So how come I decide not to link the and morning? Why this decision? So again, we would say that the decision making oracle is very intelligent. It is looking at the word in the input buffer, which is a candidate for entering into the stack. Okay, and based on this, the part of speech tag, which is imminent to enter the stack, the decision is taken. Okay, so you see how much of burden is falling on the oracle or the decision maker based on buffer. So we begin to see a complex decision making going on. Okay, so decides to shift flight. Flight has come. Input buffer is empty. Now clearly, since there is nothing to shift, at this point of time, reduction has to take place. You have to do left arcing, right arcing now. So at this point of time, I set up the relation between morning and flight. So this is a left arc. Why left? Because morning is to the left of flight. Okay, morning is to the left of flight. Now, morning and flight will have to be linked. They are linked. And since the modifier goes out of the stack, therefore morning is going out of the stack, leaving flight. The and flight are now adjacent to each other. Another between the and flight. Why left? Because the is physically to the left of flight in the sentence. The being the modifier goes out of the stack. Now I have root, book, and flight. Book and flight. Flight is coming to the right of book. So if at all any arcing is done, that will be a right arc. Okay. So and flight are linked with a right arc. Now what goes out of the stack? The the head of the arrow. The the head of the arrow goes out of the stack. So flight goes out, leaving root and book. And we know that the only arcing that is possible between root and book is right arcing, because book is dependent on right. So linked book goes out of the stack and root now remains on the stack, which is also popped. So stack empty, input word list empty, algorithm succeeds, giving you the parse tree. What is the parse tree? You can see from the last column itself: root to book, book to flight, flight to morning, and book to me. Okay, so the main verb book has two dependents, me and flight. Flight has two dependents, the and morning. Okay, and the parse is complete. So now the ball has now shifted to the court of the decision making algorithm, which is something we would like to discuss today. So this is a decision maker, and the decision maker is these days created out of a deep learning system, or the decision maker is a deep learning system. So you have the input layer where the words are on the stack, and where there is a stack which is an input for the input layer. Similarly, the buffer or the input word list is also an input for the input layer. So both stack and input buffer are inputs to the input layer. After that, there is hidden layer computation on the top two elements in the stack, the state of the buffer and state of the stack, and also the properties of the words. So you see here the words in the stack, the part of speech tags, and the arc levels. So three compartments in this deep learning network: the words, the part of speech tags, and the arc levels. Arc levels are um, the labels like n sub, d obj, subject, object, location, time, those levels. So based on that, the decision is made through computation in the intermediate layer at the outermost layer. Now the outermost layer is said to be a softmax layer. What is a softmax layer doing? The softmax layer gives you probabilities of the output. So what it does is that given the uh, given the stack and the buffer and the arc levels, part of speech tag, all this information, the softmax layer gives the probability of linking pairs of words in the sentence. Okay, pairs of words in the sentence. So this is happening at one go, though the transition-based parsing is essentially a sequence processing algorithm. So how come, you might ask a question, how come that there is this non-sequential machine? How is it operating? How is it giving the transition-based parsing? You can take a look at this paper, Chen and Manning 2014. But as we go move forward, this question will get answered, if not totally, partially. Just a minute. So I'm referring to a diagram. So looking at another machine. Okay, so you get a rough idea that the decision making is essentially a classification problem, classification between three classes: shift, left arc, right arc, and neural networks are uh, basically classifying machines. So it has the potential of doing this job, but we need more details on how it does the job. But in particular, recurrent neural networks, which are sequence to sequence transformers, they seem to be more natural technique for this problem. Okay, so then we come to learning of the transitions. Again, the material is mainly from this chapter 15, speech and NLP, but I have my own uh, thoughts, ideas, and inputs which will come here. Also, material from other books. So uh, so you recall that Book Me the Morning Flight we just now discussed involves shift, right arc, and left arc operations. Now left arc, what is the nature of left arc operation? Let's read it carefully. Assert a head and dependent relation between the word at the front of the input buffer and the word at the top of the stack and pop the stack. Okay, so so this is the left uh, the left arc operation. Right arc, assert a head dependent relation between the word on top of the stack and the word in front of the buffer. Shift the word at the front of the input buffer to the stack. And then shift is remove the word from the front of the input buffer and push it onto the stack. Reduce is pop the stack. Now, this is the basic transition based DP. So a very top level view of the dependency parsing is the following. Function dependency parse takes as input the words and returns a dependency tree. So initial configuration is state going to root, comma words, comma empty list of relations. While state not final, okay, until it's the final state. T equal to oracle state, choose a transition operator to apply. And the next state is the result of application of T on the current state. Okay, state uh, arrow apply T comma state. So this is so this is these two are the main operations. The oracle, depending on the state of the buffer and the stack, gives you the operator, and the next state is obtained as a result of operating the operator onto the state. Okay, this is a very top level view of whatever we discussed. Now, for the decision making algorithm to be able to learn what decisions to make, it requires training data. Okay, and the training data fortunately is available, inspired by the tree bank training data. The Prague dependency tree bank data was created. Okay, so please a slide again, new slide. For constituency based parsing, the training data is tree bank uh, tree bank corpus, whereas for dependency parsing, the training data is called Prague dependency parser. Prague dependency parser tree bank. So Prague tree bank and Penn tree bank. So Penn tree bank is for constituency parsing. Prague tree bank is for constituency parsing. Now, Penn is actually University of Pennsylvania in USA. Prague is the capital of Czechoslovakia. So the dependency tree is obtained, which is shown in the upper table, and the training data is shown in the lower table. So notice that notice the difference between the two examples are a bit different actually. Yeah, two examples are different. So all right. So that uh, training data has predicted action as the last column. Okay, unlike relations added in the last column for the parsing process. So the dependency parsing on the test sentence has in the last column as relations, whereas the training data table has the last column as predicted action. Now, now how does it operate? So book the flight through Houston. That it is a supervised learning situation. So book the flight through Houston is a raw sentence, and I also have the dependency parser, the dependency parse for this sentence. I have the dependency parse for this sentence. So, uh, so the way it would work is that since the dependency parse is already available, okay, I know what action to take. So route, and then the word list is book the flight through Houston. So I shift book to route. That anyway is the first action. So there is nothing much to learn here. The oracle learns that if route is the only thing on the stack in the beginning of the operations, that is, if the input word list is non-empty. Okay, so the training data can be obtained from the dependency parse trees already available. Okay, so Prague tree bank gives me the dependency data. So when there is root on the stack, that is the only thing on the stack, and the word list is non-empty, then obviously there is nothing to learn really. You shift book to the stack. Now between root and book, you know there is a dependency relation. You know this because the dependency tree is given, and you can see in front of your eye that from root to book there is an arc with head of the arc being on the book. But still the predicted action is shift, you see. What is the reason? The reason is that uh, there are more words on the sentence, and I know by looking at the dependency tree that book has dependents. Okay, book has dependents. I see it in front of me on the dependency tree. From book, there is a dependency arc going to flight. Okay, and therefore, uh, and from flight again, there are dependents. I see it in front of me in the dependency tree itself. So if book has dependents, okay, if book has dependents, then I know that while parsing, I should not take book out of the stack. Okay, I have to I know that during parsing I cannot do this, so I'll have to shift. Okay, I'll have to shift. And left arc is also not possible. Okay, left arc is also not possible uh, uh, because book is coming to the right of root. Okay, it is as if the sentence has a fictitious word in front of it called root. Okay, so left is not possible. So now I shift because that is the only operator, uh, only option available. So the has come to the stack. Between book and the, can I establish a relationship? No, I do not see any relationship in the dependency tree. You remember earlier our logic was the is a determiner and book is a verb. Determiner doesn't link directly with verb. Okay, that was the logic in the rule-based system. But in the data-driven system, I don't have to apply any logic. The data is in front of me. Okay, since I do not see any relation in the dependency tree between book and the, I again do shifting. So I shift flight. I shift flight onto the stack. Now I see that between the and flight, there is a relation in the dependency tree. The dependency tree is in front of me. So, and book is to the left of flight. Book is to the left of flight in the dependency tree. Flight is dependent on book. Okay, flight is dependent on book. But sorry, the is I have book, the and flight. Okay, and flight is on top of the stack now. The and flight, I see a dependency relationship in the tree itself, and the is a modifier. So I learn that I have to do a left arcing between the and flight and pop the out of the stack. The modifier goes out of the stack. Okay, so this I learn from the dependency tree itself. Then now I have book and flight, and through Houston is on the input buffer. So now between book and flight, I can do a right arcing, but that will take flight out of the stack. But in the dependency tree, I'm observing that there is a dependency relationship with flight through and for through and Houston. So I cannot do this. I cannot shift flight. So I cannot pop flight. So I shift more words into the stack. So through comes in. Now flight and through, I don't see any relation in the dependency tree. Okay, so I again have to shift. So I bring Houston onto the stack. So now Houston has come. So through and Houston, I see a left arc. Okay, I see a dependency relation on the dependency tree, and through is to the left of Houston. So I do a left arcing and pop through how out of the stack. Now I have flight and Houston. Flight and Houston, I learn a right arc because flight and Houston they are dependent on flight through Houston, right? So through Houston, Houston is um, Houston, flight and Houston have dependency, and Houston is to the right of flight. So I learn to produce right arc, and flight goes out of the stack. Now book and flight are there. I do a right arc, book goes out, uh, flight goes out, and then root and book remain, right arc between root and book, and then finally root remains. So this is not really parsing. Okay, the parsing has already done for me. The dependency tree is in front of me. I just observe the dependency tree and kind of simulate the parse operation for generating the training data. So the algorithm that we discussed just now, the procedure that we discussed just now, will produce these kind of predict actions. Shift, 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 left arc, shift, shift, left arc, right arc, right arc, right arc, done. So these predict actions are deciphered. I'll not say so much as learned, are deciphered from the training data. Okay, so the training, I just observe the training data and immediately the operation become uh, apparent to me. So this we call the step of generating the training data. Now that this is the training data. Okay. Now, what is that in the training data? What do I see? I see the labeling, the predicted action, the last column here are the labels. Okay. So this is like having data on the left and the class level on the right. Okay. So I have the features or things that will give me features in the first two columns, and I have the labels on the last column. So it is like a two column. It is like a two column machine learning problem where the last column is the label and the first two columns are the input. So if you'll recall that XOR, for example, was a three column problem. The last column was the label of 0, 1, etc. And the first two columns were again input 0, 1, 1, 0, 1, 1, 0, 0. So this is like that. However, uh, I have only words here, but I need generalization. Okay. Uh, Flight, Houston, book, these are all nouns. So I need that generalization or the pause tag information for the words. So this is the generalization. So is it clear to you? I hope it is clear to you. From the dependency parse, you are able to generate the training data in a convenient form, convenient for guiding the transition parsing process. Okay. The dependency parse, by the way, is processed almost as such for probabilistic dependency parsing. Okay, so while you are mimicking the dependency parse in generating the training data, you can directly process the training data and do parsing uh, in probabilistic parsing following the similar approach as probabilistic context triggers parsing. Here also, you can have a probabilistic CYK like algorithm for constructing the dependency tree. In case of probabilistic CYK constituency parsing algorithm, we set up a non-terminal between the two consecutive positions. In case of probabilistic dependency parsing, we'll set up a labeled arc between two consecutive positions. Okay, to by consecutive, I mean that after the processing of the intermediate nodes, two things come adjacent to each other. So this is the step of generation of training. Now, generations of training data are controlled by these steps. you produce a left arc relation if S1 or S2 belongs to RP. So there are there are a few symbols here, RP and RC. RC is the repository of dependency relations, all dependency relations. So if it is universal dependency relations, then you have about 20 relations, n subs, d obj, time, location, and so on. RP is the localized dependency relations. That means dependency relations which are uh, for this particular sentence and for the corresponding dependency tree. Okay, so RP is the set of relations for the current sentence and its parse tree, and RC is the whole repository of dependency relations. So what does left arc decision say? Left arc says that in the dependency tree, if you observe S1 related to S2, okay, that S1 and S2 are two top elements of the stack. So in the dependency tree, if you observe a relation between S1 and S2, then you put the label as left arc. Okay, put the label as left arc in the training data. And right arc is the predicted label if S2 or S1, not S1 or S2. S1 is to the left of S2. S1 is to the left of S2. Now S2 to R, S1, if you see a relation in the dependency tree, which is presented to you, RP, and for all R dash, uh, R dash comma W such that R S1 R dash W belongs to R, then S1 R dash W belongs to RC. So that means if you observe the dependence of S1 in the dependency tree, okay, then you can recursively uh, uh, post those relationships from the localized parse tree into the RC, okay, the repository of dependency relations. And if neither of these two operators are applicable, left arc and right arc, then you shift. So these rules, okay, these rules are applied to generate the training data. Now the generated training data will be used for machine learning, okay, used for training an oracle. But you don't have to do meta learning. Okay, you don't have to learn this rule for generating the training data. Generation of training data is rule governed because you are very close to generating the training data. The dependency tree is there in front of you. You are essentially converting the dependency tree into a convenient form which is consumable by a machine learning algorithm. That machine learning algorithm produces the oracle for the transition based parsing, transition based parsing. Okay, so these are the rules, and these rules you can study more carefully. It essentially captures the intuition that uh, don't set up the uh, right arc if you see that the dependent is itself a head for other dependents. Okay, that is the rule which is specified here. So
Sir, could you again explain the right arc rule?
yeah, right track rule. So if so S1 and S2 are the two top elements in the stack. Okay, so if so S1 is on top of the stack and S2 is the element below it. Now if I find that between S2 and S1 there is a relation in the dependency tree given, and for all R dashed comma W such that S1 R dashed W belongs to RP. What does that mean? S1 is the S1 is the top of the stack. Okay, and between for S1 you have other words which are related to S1. Okay, in the dependency tree which is in front of me, which is given to me as data, then S1 R dash W will be added to RC. Okay, will be added to RC. So this rule, the contrapositive of this rule. Okay, so it is an AND condition. Okay, it's an AND condition. So if not, any of these conditions, in particular the second clause, if it is false, okay, if it is false, then this rule is not applied. Okay, and when you and we are predicting only the labels. We are generating the training data, so we are predicting these labels here. Okay,
Sir,
okay.
shouldn't it be like at least one rather than for every R dash W?
It should be there exist. You are saying.
Yeah.
Let me think. Let me see. Okay.
Okay. Sir.
Let's finish the top level description. Then I think refinements will do. So we are doing essentially the generation of training data. So all this is towards a classifier which will be trained on this training data. Okay, I'm generating the training data. So this training data will train a classifier, and then this classifier will need features. So for example, if you have a sentence cancelled flights to Houston, then the features are s1.w is equal to flights. That means the top of the stack is the word flights, and then the operator should be shift. The second element of the stack is cancelled. Okay, operator is again shift. The part of speech tag of the first element on the stack is NNS, that is plural noun. Then the operator is shift. The second element's part of speech tag is VVD, that is past tense verb. Now you see cancelled has become the second element on the stack after pushing flights onto the stack. Then again the operator is shift. B1 is the first word in the input buffer. If the word B1 is 2, the word B1 is, then the operator is shift. If the part of speech of the word in front of the buffer is 2, which is the to preposition, then the operator is shift again. And if the first element on the stack has word feature as flights and post tag feature as NNS, then operator is shift. Okay, so we will understand this more carefully with more refinement and detail. I'm just giving you the first level understanding of feature engineering. Okay, the feature engineering is done this way in terms of the stacks word value and stacks part of speech value, amongst many other features. Similarly, the input buffer words word value and feature value, amongst many other features. So those features are gradually being built so that such a machine can be trained for producing the labels. So I hope you are beginning to see that there is a training situation arising. Training data easily obtainable from the dependency tree. How do you get the dependency tree? That is the more difficult part. You have to employ people who sit down with the sentences, work on an interface and produce this right level, left level. Okay, right. They do only right level and left level. Shifting has to be deciphered from the training data and the input sentence. Now, when we go across languages, this basic framework needs some adjustments. So if you look at this sentence, people in front of the house told me. The Marathi sentence for this is interesting. घरा समोरच्यानी मला सांगितले. घरा समोरच्यानी मला सांगितले. And if you look at the Hindi sentence, that is घर के सामने ने मुझे बताया. I am writing it in Roman script so that people who have any difficulty with Devanagari, they also can read it. So the interesting case is a Marathi. Ghara samor chani mala sangitle. Can somebody verify that you're looking at 3 sentences in 3 languages on the screen?
Yes, sir.
Okay. Ghara samor,
Yes.
yeah, okay. Ghara samor chani mala sangitle. Mala is mujhe, to me, okay. Sangitle is past tense verb, told. And see the phenomenon of language characteristic difference. Marathi is what is called agglutinative. Ghara samor chani is actually all these 4. Ghar ke samne walon ne. In fact, walo also written in Hindi separately. So 1, 2, 3, 4, 5. 5 morphemes are glued together. Okay, they are stitched together to form one single word in Marathi. Ghara samor chani. मला सांगितले मुझे बताया. मला सांगितले मुझे बताया is just one-to-one transformation. People in front of the house. Okay, now people is an interesting introduction here. It is not there in either Hindi or Marathi. But English cannot be English. English is subject compulsory language. Okay, it needs a subject compulsorily, mandatorily in the sentence. So you could have written those in front of the house told me, or people in front of the house told me. Sangit le indicates plurality, so more than one person. Ni also indicates plurality, more than one person. Walon is a suffix indicating plurality. So Hindi, Marathi are plural. They show plural suffixes, and people is inherently a plural noun. Okay, plural noun. So we have this interesting case. Now, in English, you have 1, 2, 3, 4, 5, 6, 7, 8 words. 1, 2, 3, 4, 5, 6, 7, 8. In Hindi, 1, 2, 3, 4, 5, 6 words. But walo, if it is written separately. Mm, so if there is a native speaker of Hindi in the class, can you tell me samne walo is written together or separately?
Together.
Together. Okay. One more
In
in
Hindi, it should be separate.
so that is the difference.
Yeah, I guess it
Yes,
should be
sir. It should
separate.
be separate.
It should be separate.
अच्छा, so this will be 2 words then. Okay, घर के सामने वालों ने मुझे बताया. See, I am a native speaker of Bengali. Okay, so that's why native speaker intuition is extremely important. Speaker who are born in that language, grow up in that language, their decision is final, and their intuition is to be respected. Now, of course, Hindi has many variations, and that's why I probably heard 2 different decisions. One of you said Samne Walo is written together, and 2 of you said no, they are written separately. Okay, can I have one more opinion? Is there another Hindi speaker in the class, in the attendees today?
It
Yes,
should
sir.
be separated.
Who is this?
Separated. Shubham.
And you are a native Hindi speaker?
Yes, sir.
It will be written separately. Samne Walo.
Yes, sir.
Acha.
Sir,
I think.
even if you listen to the song Mere Samne Wali Khidki, but Wali is written separately, so I'm guessing Walo should also be written separately. This is a plural in that case.
Okay, okay. So 1, 2, 3, 4, 5, 6, 7, 7 words. So there will be 7 shifts into the stack, but in Marathi there will be 3 shifts into the stack. You see, Ghara samorchi ani mala sangitle, only 3 words, and then there will be a dependency from Ghara samorchi ani to sangitle. Sangitle is the main verb, so root to sangitle, and straight away the whole thing Ghara samorchi ani will have a from sangitle to Ghara samorchi ani there will be an arc, and sangitle to mala also there will be an arc. So these dependency tree will be very simple. One root word and 2 dependents. Whereas people in front of the house told me 8 words. घर के सामने वालों ने मुझे बताया 7 words. It will have many more nodes in the dependency tree and many more arcs. But what Marathi did is not really Very useful. You have the same problem for all agglutinative languages. Tamil, then Manipuri, Hungarian, Turkish, Arabic, Hebrew. Okay, everywhere the dependency parsing tends to produce very small number of nodes, but that's not enough. Okay, from that you will not be able to conduct large scale downstream NLP applications. You need more information. You need a dissection of the words and obtains relationships prevailing within the morphemes. So you will have to do what is called segmentation. Okay, so segmentation is a lower level NLP task before dependency parsing that has to be done. So I think I've taken a long time. I have just 3 minutes for questions. So any questions?
Quite a lot, sir.
Quite a lot. Oh, okay. Maybe I can answer only one or two and rest.
Yes. I'll repeat these questions in the next class. So Rishi asks, I think that both the sentences in the athlete example are projective. There should be intersecting edges for non-projectivity, right?
Intersecting is a deceptive notion. If you draw the diagram cleverly, maybe you can avoid intersection. No. The actual definition of projectivity is what is written. I think we need a little modification here. An arc from a head to a dependent is said to be projective if there is a path from the head to every word that lies between the head and the dependent in the sentence through the dependent. Okay, you have to first go to the dependent and then try to come to the words, intervening word.
Continuing this discussion, he also asks, projectivity is required in transition-based parse because we always find a relation between the top two adjacent words in the stack, right?
Yes, that's true. That is true.
Varad asks the question, the oracle in transition-based parsing is learned from data or using rules. Is learned from data or using rules. A wrong decision can lead to errors in other relations as well, right?
Both. And if you look at today's dependency parsers, they are all data driven.
Right.
That means the oracle is data driven and it is learned from the dependency parsers.
Okay.
One more
Should I
question.
take one more?
One
For
more.
left dependent arc, why is the head coming from input buffer? We have assumed that the head and modifier are both in the stack, right?
Yeah, so we'll go with the completely stack based operation. I think you are referring to the description of left arc and right arc. Right arc says also look at the front of the input buffer. No, I think we will work with only two elements on the top of the stack. Okay, so yes, we'll have to now close the class. Huh? Thank you.